We've run into descriptions in the past of describing curves in the xy plane as functions of x, which pass the vertical line test. Okay, so for each value of x, you get one value of y. We've also considered curves that pass the horizontal line test, and there we saw that we could describe these curves as functions of y, and so each value of y gets one value of x as output. And now we're going to generalize this concept by using parametric equations, okay? And so consider any general curve in the xy plane now. What we're going to do is use an extra axis, okay? It's not going to be a function of x or a function of y, but a function of t, the t-axis, an arbitrary variable t, okay? And you could think about this as being the time axis. And so for each point on this blue curve, okay, it's going to have some x, that's an x, right, and some y, okay? But this time we're going to make x and y functions of t. So we're going to have an extra t value there, okay? And so for any given, say, t naught here, okay, then that point t naught maps on to this x and that y, since both x and y now are functions of t, okay? And so perhaps at a later time, say t1, we'll have this point up here. So t1 would map to x t1, y t1. And you could think about this t-axis as a function of time and this xy plane as a trajectory of some particle moving in time. Okay, that's how I think about them, at least. Okay, and we have bounds, so our domain here is t now, and it's between a and b. T is called the parameter, and the curve that you get from following x and y as you progress through t is called the parametric curve. Okay, it starts with the initial point here at the beginning of the interval and ends at the end there at the end time. Positive orientation is the direction that you move in as you're increasing t. Okay, and so you know, if t was progressing and we're going this way, then positive orientation will be that way. But if t is increasing and we're going towards the y-axis, then it would be the opposite direction. So let's look at a very basic form of parametric equations, and that's for a line. And any line could be described by the following parametric form. So x is x naught, where x naught is a constant, plus a, another constant t, the parameter, and likewise for y. And if it's a line that extends infinitely in length, it's going to go from minus infinity to plus infinity. And if a is not equal to 0, okay, then what we'll get is a line that has a slope b over a and passes through the point x naught, y naught. Okay, so this is the general form for these type of lines. If a is equal to 0, then we just get a vertical line. Okay, in that case we would get a vertical line that runs vertically at x equals x naught. And so let's take a look at a concrete example of that. So here we have these two parametric equations. X is equal to this and y is equal to that. And t runs from minus infinity to plus infinity. And we're going to, what we'll do to get a description of this in the xy plane is first solve for t in terms of x, and then plug that t into the equation for y. Okay, and so here's what I get when I plug it in to the equation for y, and I end up with that equation there. And as you could see, it is it's the line with slope -2 that passes through the origin there. Okay. Another way we could have looked at this is to use the basic outline that we have above here. Okay, a does not equal 0 there, and so b over a would be -6 over 3, or -2, so that's the slope, and it runs through the point -2, 4. Okay, and -2x definitely runs through the point -2, 4. And so that's another way we could have looked at this equation. Now, parametric equations do not describe a unique curve. You could get multiple parametric equations that describe the same exact curve. And so if we look at this example here, we want to find two sets of parametric equations for the line of slope 1/3 that passes through the point 2, 1. We're going to use this general outline. Okay. So one way to get a slope of 1/3, and recall that the slope is b over a. So we're going to choose b equals 1 and a equals 3. And we want to run through the point 2, 1, so we'll set x naught to 2 and y naught to 1, and we get these parametric equations. Now, as long as our ratio was equal to 1/3, the equations will work out. So another way to get a ratio of 1/3 is to have a equal to -6 and b equal to -2. And so this description describes, these parametric equations describe the same exact line. They both run through 2, 1, and they both have a slope of 1/3. I should note that here, as t increases, x decreases, and likewise for y. So if we draw this out, very crudely there, okay, here's the point 2, 1. So that's our line there, okay. But the top description, so over here, the orientation is going to the top right, and whereas this bottom here, the orientation is going down. Okay, so that's something to keep in mind. Let's also look at descriptions of circles. So we want to show that what we have there for parametric equations give you a circle, and with period 2 pi over b. How do we do that? Well, we'll just take each of these equations, we'll subtract x naught from the right hand side, and we'll do the same thing with y naught, and we end up with these equations here. Now, when we square and add these together, we get this result. Factor out an a squared, and you'll get cosine squared bt plus sine squared bt. Well, that's just equal to 1, right? This part here is equal to 1. And so your final result is a squared. And how do we know that it has period 2 pi over b? Well, notice that if you take t is equal to 2 pi over b and multiply it by b, you get 2 pi. And so you've gone around the circle once, right? The circle has 2 pi radians, so you've gone around once when you hit time 2 pi over b, and so that's equal to the period. This b is sometimes called the angular frequency. In physics in particular, it's called the angular frequency. Finally, let's see how a point on the rim of a wheel rolling would look like. Okay, we get these parametric equations for that, where time is greater than 0 and A is strictly positive. The motion that you get from tracking a point along the wheel is called a cycloid, and let's take a look at how that looks. Okay, so what you're seeing here is the cycloid, and you can see the parametric equations for it. We have x is equal to a times t minus sine t, and we have y is equal to a times 1 minus cosine t. And you could see that these x and y versus t. Okay, so on the top you'll see x versus t, how that looks, and on the bottom left there you'll see how y of t looks. Now what happens when we put these together and have a t-axis as and plot the point x, y in the xy plane as we're moving along t? Well, let's do that. So we increase t, and so as we increase t, you could see the blue dot there is following what y is, and the green dot is what gives us what x is. And we plot the x and y for each respective t, and you could see that we're moving along this point on the rim, and we get that cycloid. And this should clarify for you the concept of parametric equations, that you basically have now two functions, both of them with respect to t, one for x and one for y, and you plot for each t that point xy in the xy plane to get something that looks radically different, right, than the functions for x and y. You get a cycloid there, and the other ones are, functions of sine and cosine, and one of them has additional t in there. So they look radically different, but the cycloid is what we'll get when we just take a given t, find the x for that t, find the y for that t, and then plot it on the xy plane.